Hi everyone, in this video I'm going to talk through my machine learning workflow for the Abelo dataset. The target here is rings, which is commonly used as a proxy for age. So our goal is predict rings as a continuous number that is a regression problem. So first the dataset was loaded from UCI and I get X as a feeder and Y as the target rings. The dataset had 4,177 rows, and the feeders includes one category variable, sex, and a physical measurement like a length, diameter, height, and several weight variables. And before even modeling, I check some basic quality for the missing value and the duplicate, so which is good that there's nothing. When I look at the distribution plots, a big thing jump out is some variables are skewed, and the height especially look like it has extreme outliers and a strong right tail. This is important for workflow because outliers can distort errors and can cause some models to behave badly, especially models can try to fit exact boundaries. In a pairwise scatter plot, I noticed a very strong relationships between variables. For example, the length and the diameter are moving together, and the weight variables are also highly related. Therefore, there's a multi-collinearity, which means that if I use linear regression, the coefficient might become unstable and hard to interpret. And then for the correlation heat map, it is very helpful for intuition. The rings correlate most with shell width and with diameter, length, and hole width. So my first hypothesis is older abelos tend to be bigger and have a heavier shells. So looking at the rings histogram and box plot, the most data are around 8 to 11 rings, and there's a long tail going up to about 29. The maximum for rings is 29. Because there are fewer very old examples, the model may perform well in the middle but struggle at the extremes uh, data. Uh, then I convert sex into numerical values using label encoder. One thing needs to be aware of is a label encoder creates an artificial order like 0, 1, 2, but sex is nominal. So if I wanted the most correct setup for linear models, I prefer one hot encoding, which means that the tree models are usually less sensitive to the assumption. Next, I slip the data into train and test about 80 to 20. This is important because I want an unbiased evaluation on unseen data. Then I apply the standard scalar because I fit the scalar on the train set only and then transform both train and test. This will prevent the data leakage. So which means if I fit scaling on the full data set, the set distribution leaks into the training. And also, I scale Y during training for stability in some models and convert predictions back to the original rings scale using inverse transform. This way, my final metrics are still in the real unit rates. For validation, these notebooks use a single holdout test set. This is a valid baseline and makes the model comparison straightforward because every model sees the same train and test split. However, holdout can be sensitive to randomness. So a stronger approach, will be k-fold cross validation. But in this baseline run, I'm using holdout and focusing on comparing model families and diagnosing behaviors. And now the model section, I intentionally compare a mix of models so I can learn both performance and behaviors. So the MLR is a natural baseline for numeric target, and Rage Lasso Elastic Net help handle multi-collinearity and control complexity. So in ML workflow, these are controlled models, which is easy to train and interpretable and often strong baselines. When I look at in MLR, I see the general upward trends, but predicts time to shrink extreme values toward the center. This is common when the dataset have fewer extreme examples. Then for Rage, it looks very similar, which makes sense because it stabilizes coefficient but doesn't necessarily change predictions dramatically if the baseline is already reasonable. They are useful because the true relationship between physical size and range may not be perfectly linear. And then for KNN, a model is local and depends heavily on scaling, so it benefits from standardized and it can capture local patterns, but still struggles in compares regions like very old rings. Then SVR model with a polynomial kernel can capture nonlinearities, but is sensitive to hyperparameters and can underperform if not turned carefully. Then for MLP, MLP can also model nonlinear structure. In the workflow term, it will flexible, but it needs careful tuning and enough data signal. Here it looks competitive, not very dramatically better. Finally, for the decision trees, this is a classic tree-based baseline. The plot looks like chunkier and less stable, which is a warning sign. Single trees often overfit, especially with noise measurement and outliers. So from all these outputs with these models, MLR is the best model for this notebook. After comparison, I want to interpret that I train a random forest and check feeder importance. This plot clearly shows the shell width as the most important feeder, and the sex is not the least important. This mesh earlier EDA that the correlation heat map already hint shell width is strongly tied to rings. So in ML workflow, this is a good example for the closing the loop. And then I want to connect this to the bias of variance trade-off. A decision tree tends to have a low bias but high variance. It can fit complex patterns, but it overfits noise and doesn't generalize well consistent with the messy plot. And for Lasso, with the strong shrinkage and increased bias by oversimplifying the relationship with leading to underfitting. For MLR and Rage, it usually offer a more stable middle ground, which is have a moderate bias, lower variance, and a decent generalization. About the logistic regression, because the rings are continuous values, so it is not the right tool for this notebook. It's designed for classification, not a continuous regression. Finally, the takeaway from the assignment is I would add k-fold cross-validations for more reliable model comparison and use one hot encoding for the sex for linear models. Thank you for listening.